We're now going to talk about the measurement of heat, and basically the measurement of heat, the technique for measurement of heat is known as calorimetry. And there are two ways we can do measurement of heat. We can do it directly in terms of work, or we can do it by comparison. For example, here we have a system B, which is a copper block. So this is a copper block that is in thermal contact with system A. So this is a thermal contact here. So we allow heat exchange, heat can flow, and system A is consisting of a resistor, thermometer and water inside a container, and we can basically change the internal energy of system A by using this battery and the switch S, and battery that has an EMF of V volts. So in the system, external parameters of B is fixed. So you can see that there won't be any work done on B. So we have W is equal to 0. So B basically has a thermal interaction with system A. So there is a thermal contact between A and B. And I call Q sub B the heat that is absorbed by system B. And initially I have A and B in thermal equilibrium. So initially, before I close the switch, I'm going to have a thermal equilibrium so that I form my reference macro state, and there is a reading in the thermometer L sub A. This is for macro state A, which is the initial state. And then we close the switch. When the switch S is closed, there will be energy transfer from the battery to the water through the resistor. So it is closed and opened, and we wait for some time. Now A plus B, or let's say A and B, will reach thermal equilibrium, and I have another reading on the thermometer. The new reading, L is equal to LB, for the new thermal equilibrium state for macro state B. And the system A plus B is thermally isolated, so I don't have any thermal interaction, any heat transfer from the surroundings. Now you can see that the energy that I'm providing to the system A plus B is the electrical work. So it's going to affect the mean internal energy of system A and the mean internal energy of system B. So this is the total amount of energy that I'm transferring to system A and B. So W transferred to A and B. But there is no work done on B. So if you look at delta EB bar, this is just equal to the amount of heat absorbed by B, because W on B is equal to 0. So external parameters are fixed. Therefore, from this equation, I can see that the heat absorbed, QB, is equal to W minus the mean internal energy change of system A. And if you choose system B, if system B is much larger than A, many more degrees of freedom, much larger than A, in this case, the mean internal energy of system A will be much less than W. Most of the energy will be transferred to system B in the form of work. So delta EB bar, which is the heat absorbed by system B, according to first law of thermodynamics, when there is no external work, it's just the heat. This will be approximately equal to the work that is electrical work that is being done by the circuit that we have connected to system A. So that's one way of determining or approximately determining W. Or QB, the heat absorbed by the system B. You could also calibrate system A, the length readings as a function of the mean energy change in system A, and even without this approximation you could obtain the heat absorbed by the copper block in this experiment. An alternative way to do this is measurement by comparison. Again, I have a system C, which is a copper block here. System B is water and the thermometer. Here I have B plus C thermally isolated. So there will be only thermal interaction between B and C. So this is a thermal contact between B and C. So I have heat absorption for system C possible, and heat absorbed by system B plus the heat absorbed by system C should be equal to 0, because the heat absorbed by C is the heat released by B. So if I have a reading in the thermometer as 0 before putting the copper block, and then if I have a reading after reaching thermal equilibrium, after putting the copper block inside the water, thermal equilibrium, so we have to wait enough, have to give it enough time to reach thermal equilibrium. Since we know how the mean internal energy of system B depends on temperature, or how it depends on the length L, so we know this, the change in the length of the thermometer will tell us how much the heat absorbed by system C is. The change in the mean internal energy of system B is the heat absorbed by B, which is equal to minus the heat absorbed by C. So we have a reading, the delta L tells us the change in the mean internal energy of B. It also tells us minus QC, the heat absorbed by the copper block in this process. So the technique with which we're measuring heat is called calorimetry, and we can do measurement of heat in terms of work. For example, when we have a copper block in thermal contact with a container that is filled with water, and the thermometer and the resistor is inserted inside. When we form a contact with the switch and the circuit, the electromotive force will create a current that flows through the circuit. There will be a DC current flowing I for an amount of time delta t, in which that's the period where the switch is closed. the electrical work done will be transferred to the water as heat, because there will be a thermal contact between the resistor and the water, and we will see that the temperature of the water will rise. If we have the thermal contact between A and B, then the electrical work done will cause a change in both mean energy of A and B, or the system A plus B. And since B is only in thermal contact with A, there is no external parameter change for system B. Work done is zero. There is only heat absorbed by B. Heat absorbed by B is the work provided, electrical work provided, minus the mean energy change of system A. And if system A is much smaller, this heat absorbed will be approximately equal to the electrical work done. And similarly, we can do measurement of heat by comparison. If we have a situation where we reach thermal equilibrium with water and a thermometer, we can have an initial reading, and then if we insert a copper block inside and wait for thermal equilibrium, we have another reading, our final reading. If we know how the mean internal energy of system B varies with temperature or varies with length, since the mean internal energy change of system B is heat absorbed by B, because external parameters are fixed, it will be equal to minus the heat absorbed by C, or heat released by C. So if you have a reading of the change in the length of the mercury column, you can basically get a reading of the heat absorbed by C. Because of this calibration, we know how the mean internal energy varies with length.